Okay, we're going to go ahead and start the lecture over section 8.3 on inverse trigonometric functions. Okay, so in section 8.3, this is where we learn to understand and use inverse sine, cosine, and tangent functions. For a trigonometric function, a domain value is an angle measure, and the range value is a ratio. For the inverse of a trigonometric function, the domain value is a ratio, and the range value is an angle measure. So I'll draw an example, a simple example of a right triangle. And I'll label this acute angle theta, and the sides, the lengths are 3, 4, and 5. So we can write that the cosine of theta is equal to 4/5, and the sine of theta is 3/5, and the tangent of theta is 3/4. So for each of those, cosine, sine, and tangent, the domain value is an angle measure, and the range value is a ratio of numbers. Okay, but in terms of the inverse of cosine will have an input value of 4/5, and it will give us the output value theta. And for sine of theta equals 3/5, the inverse of sine will have an input value of 3/5 and an output value of theta. And the same for tangent. Since tangent of theta equals 3/4, the inverse tangent will have an input value of 3/4 and an output value of theta. I'll go ahead and use the inverse notation that I'll discuss in a second. If cosine of theta is equal to 4/5, then theta is equal to the inverse cosine of 4/5. Inverse cosine also is equivalent to saying arc cosine. You'll see both of those notations in the textbook. And if sine of theta equals 3/5, then theta is equal to the inverse sine of 3/5. Or equivalently, theta is equal to the arc sine of 3/5. The same is true for tangent. It has an inverse. Tangent of theta equals 3/4. So theta is equal to the inverse tangent of 3/4, or the arc tangent of 3/4. Okay, so you got a preview of the inverse function notation. If f of x equals sine of x, then f inverse of x is inverse sine of x, or arc cosine, or arc sine of x. The variable y is interchangeable with f inverse in this setting. And the same in the next line. If g of x equals cosine of x, then g inverse of x is cosine inverse of x, or arc cosine of x. if k of x equals tangent of x, then k inverse of x is equal to the inverse tangent of x, or the arctangent of x. And just like you learned in college algebra or another algebra class, the inverse notation, it looks like it has an exponent of -1, and it's in the position of an exponent, but for an inverse function, it doesn't mean inverse or the reciprocal. So inverse, for example, the inverse sine function does not equal 1 over sine of x, and so on. Okay, in general, if y equals f of x is a 1-to-1 function, then f inverse of x exists as a function and is itself a 1-to-1 function. So this, you might remember this, if f of a equals b, that is for the function f, the input value is a and the output value is b. For the inverse of f, f inverse of b equals a. So the input value for f inverse is b and the output value for f inverse is a. Okay, but the trigonometric functions are not 1-to-1 functions. None of the trigonometric functions pass the horizontal line test. So, for example, if you sketch one period of sine, so it looks something like this. So those are pi over 2, pi, this is 3 pi over 2, and 2 pi. This is just a graph of y equals sine of x. Well, it fails the horizontal line test. So y equals sine of x on its full domain is not a 1-to-1 function. But just like we did in college algebra, we can restrict the domains of functions so that they are 1-to-1 on those domain restrictions. So we do that with sine of x, y equals sine of x, y equals cosine of x, and y equals tangent of x. We will restrict the domains so that those functions are 1-to-1 functions. Okay, so we'll begin with y equals sine of x and its inverse, y equals inverse sine of x. So on the top left, y equals sine of x, we're going to restrict the domain of sine of x to the interval from negative pi over 2 to pi over 2. And the range of y equals sine of x on that restricted domain is from -1 to 1. This is the same range for y equals sine of x on its full domain. But we'll just sketch a graph of y equals sine of x on the restricted domain from negative pi over 2 up to pi over 2. And the range is from -1 to +1. So our restricted y equals sine of x will look like this. And on that restricted domain, y equals sine of x is a 1-to-1 function. Okay, so for y equals inverse sine of x, its domain is from -1 to 1. It's the same as the range of y equals sine of x. And the range of inverse sine of x is from negative pi over 2 to pi over 2. This is the same interval as the restricted domain of sine of x. So we'll also sketch a graph of y equals inverse sine of x. The domain is from negative 1 to 1. And we could use the graph of y equals sine of x to help us. On the graph of y equals sine of x, we have the ordered pair negative pi over 2, negative 1. So that means on the graph of y equals inverse sine of x, we just interchange the x and y coordinates from y equals sine of x. And we'll have the ordered pair negative 1, negative pi over 2 on the graph of the inverse. The point 0, 0 is on the graph of y equals sine of x. So 0, 0 is also a graph on inverse sine of x. And from the graph of y equals sine of x, we have the ordered pair pi over 2 to 1. So on the graph of y inverse, or a sine inverse of sine, we have the point 1 pi over 2. So it's this point up here. And the graph of inverse will have this shape. Okay, so one of the key points to remember whenever you're using the inverse sine of x is that the range is from negative pi over 2 to pi over 2. You'll see a little bit later why it's important to remember that. Okay, for y equals cosine of x, we're going to restrict the domain to be between 0 and pi, and the range will be from negative 1 to 1. Okay, so on the interval from 0 to pi, so we have a range from negative 1 to 1. So we remember what y equals cosine of x looks like in general, but on the restricted domain from 0 to pi, it will just be this part. Okay, so on this restricted interval, cosine of x is a 1-to-1 function. Okay, we'll sketch the graph of the inverse of cosine. So the domain is from negative 1 to 1 again. But the range, the domain of inverse cosine is negative 1 to 1, and the range is from 0 to pi. So I'll put in an intermediate point, pi over 2, and pi. From the graph of y equals cosine of x, we have the ordered pair pi 1. So on the graph of, pi negative 1. So on the graph of inverse of cosine, we have the ordered pair negative 1 pi. So negative 1 pi is a point on the graph. On y equals cosine of x, we have the ordered pair pi over 2, 0. So 0 pi over 2 is a point on the graph of the inverse. And then on the graph of y equals cosine of x, we have 0, 1. So that means on the graph of the inverse, we have 1, 0. Okay, so then we connect the dots. The graph will have this shape for y equals inverse cosine of x. Okay, for y equals inverse cosine, it's important to remember that the range is from 0 to pi. Okay, tangent of x, y equals tangent of x. The domain restriction for y equals tangent of x is from negative pi over 2 to pi over 2. And the endpoints are excluded. That's where the y equals tangent of x has vertical asymptotes. So from negative pi over 2 to pi over 2, and remember the vertical asymptotes. So on this domain, on this restricted domain, tangent of x is 1 to 1. So it has this shape roughly. Goes through the point 0, 0. For y equals inverse tangent of x, the domain is all real numbers from negative infinity to positive infinity, and the range will be between negative pi over 2 and pi over 2. So the inverse function has horizontal asymptotes. At negative pi over 2 and pi over 2. So horizontal asymptotes for the inverse. And the graph of the inverse will look sort of like this. Okay, we'll use the inverse notation. We'll practice a few basic examples. Okay, we know that sine of negative pi over 2 is negative 1. And so that means, well, in this case, it means that the inverse sine of negative 1 equals negative pi over 2. Cosine of 3 pi over 4, that's equal to the negative of the square root of 2 over 2. 3 pi over 4 is in the second quadrant. And so cosine is negative in the second quadrant. So the inverse cosine of negative square root of 2 over 2 is equal to 3 pi over 4. So we have to remind ourselves that the range for inverse cosine is between 0 and pi. 3 pi over 4 is between 0 and pi. The tangent of pi over 3, that's equal to the square root of 3. And the inverse tangent of the square root of 3 is equal to pi over 3. Okay, it's possible to think this is, in general, easier than it really is. Each of the input values for sine, cosine, and tangent were values or R values that are in the ranges of their corresponding inverse functions. So in this case, negative pi over 2 is in the range of inverse sine. In the next example, 3 pi over 4 is in the range of inverse cosine, and pi over 3 is in the range of inverse tangent. So a little bit later today, you'll see why I'm pointing that out. Okay, in this next exercise, suppose the lengths of two shorter sides of a right triangle are given. Show how the measures of the two acute angles can be found. Okay, so we have a right triangle. And let's label two acute angles. I'll label one alpha and one beta. And we're given the lengths of the two shorter sides. So let's call those A and B. So just to reiterate, A and B are given quantities. And that's enough information to find the values of alpha and beta. Okay, the first thing we can do, well, there's more than one thing that we can do, but perhaps the most straightforward thing to do, we can use the tangent function. The tangent of alpha in this right triangle is equal to the length of the opposite side divided by the length of the adjacent side, so B over A. And then if we take the tangent of beta, that's equal to A over B. Remember that A and B are known quantities, so if tangent of alpha equals B over A, then alpha equals the inverse tangent of B over A. And similarly, if tangent of beta equals A over B, then beta equals the inverse tangent of A over B. So notice we didn't even need to find the length of the hypotenuse. Okay, on the next page, we'll discuss compositions of trigonometric function, of a trigonometric function and its inverse. Okay, this says if f of x is a one-to-one function, then the f inverse exists. What that means, this is the function notation for f inverse, so it means that the inverse is a function. Every function has an inverse, but not all inverses are functions. Okay, f inverse of f of x equals x for every x in the domain of f. And the composition works in the other direction. F of f inverse of x equals x for every x in the domain of f inverse. Okay, so if we compose sine of inverse sine of x, well, that's just going to be equal to x for x values between -1 and 1, including -1 and 1. So this works the way that we would expect it to. And inverse cosine of x equals x for all x between -1 and 1. And the inverse tangent of x equals x for all x between -infinity and +infinity. Okay, but it gets trickier if we compose in the other direction. We have to be more careful. So if the outer function is an inverse sine or inverse cosine or inverse tangent, special care must be taken. The inverse sine of x will equal x, but only if x is between -pi/2 and pi/2. And why is that? This is because the range of inverse sine is from -pi/2 to pi/2. So it's possible, well, we'll see a little bit later, but well, I'll just hold my comment until later. Okay, the same sort of restriction occurs if you have the outside function being the inverse cosine. The inverse cosine of x equals x only when x is between 0 and pi. And if the outer function is inverse tangent, the inverse tangent of x equals x only for values of x that are strictly between -pi/2 and pi/2. Okay, so let's try that out on some specific examples. Evaluate the following. The inverse sine of the sine of 3pi/2. Well, this cannot be 3pi/2 because 3pi/2 is not in the range of inverse sine. So what do? Well, one thing you can do, like in a case like this, we know that one thing we know, 3pi/2 is a special angle. Sine of 3pi/2 equals -1. So this is one of those values to learn by heart. So we can do this in steps. Inverse sine of 3pi/2 is equal to the inverse sine of -1. And the inverse sine of -1 equals -pi/2. Because the range of sine is from -pi/2 to pi/2. Okay, let me write in up here what the range of inverse cosine is. Well, it's right there, but I'm just reinforcing the concept. The range of inverse cosine is the interval from 0 to pi. Okay, so in this next example, evaluate the inverse cosine of -pi. Well, this can't be equal to negative pi because negative pi is not in the range of inverse cosine. So what do? Well, we know how to evaluate cosine of negative pi. So here we can employ a couple of things. Cosine of negative pi, we know that cosine is an even function. So cosine of negative pi equals cosine of pi. And we also know that cosine of pi equals -1. Okay, so we can rewrite this as inverse cosine of -1. And inverse cosine of -1 equals pi. Okay, let's try tangent. So just to reiterate, the range of inverse tangent is the interval from -pi/2 to pi/2, excluding the endpoints. Okay, so the inverse tangent of 2 pi cannot be equal to 2 pi because 2 pi is not in the range of inverse tangent. Well, we do know that tangent of 2 pi, we know tangent of 2 pi, we can think of this in a couple of ways. Remember that tangent is sine over cosine. So tangent of 2 pi is sine of 2 pi divided by cosine of 2 pi. And we know that sine of 2 pi is equal to 0. And we know that cosine of 2 pi equals 1, and 0 divided by 1 is 0. Okay, so inverse tangent of 2 pi is equal to the inverse tangent of 0. And the inverse tangent of 0 is 0. Okay, so I'll reiterate something. If you're composing a trigonometric function with its inverse, well, if the trigonometric function, like sine, is the outside function, and the inside function is inverse sine, then sine of inverse sine of x is x. Similarly with cosine and tangent, if cosine is the outside function and inverse cosine is the inside function, then cosine of inverse cosine of x will equal x, provided that x is in the intervals. And if the outer function is tangent and the inner function is inverse tangent, then the tangent of the inverse tangent of x equals x for all x between -infinity and +infinity. But when the inverse function is the outside function, that's where you have to be careful, as we saw in those 3 examples. Okay, we'll review the cofunction identities. Remember from section 7.2, the cofunction identities. Cosine of theta equals sine of pi/2 minus theta. And it works in the other direction. Sine of theta equals cosine of pi over 2 minus theta. Tangent of theta equals cotangent of pi over 2 minus theta, and cotangent of theta equals tangent of pi over 2 minus theta. Okay, so those are things that we already learned. These are very useful to remember, those cofunction identities. So suppose we have an angle theta that's between 0 and pi. So take special note that theta is between 0 and pi. Then the inverse sine of cosine of theta, well, if we use a cofunction identity, we're going to replace cosine of theta with sine of pi over 2 minus theta. Then the inverse sine of pi over 2 minus theta equals pi over 2 minus theta. And that's because pi over 2 minus theta is between negative pi over 2 and pi over 2. So you can see that if you reason it out this way. We're beginning with theta between 0 and pi. So pi over 2 minus each of those endpoints will give us the range for pi over 2 minus theta. So I'll try to work this out. We're given that 0 is less than or equal to theta, which is less than or equal to pi. And I want to prove to you that pi over 2 minus theta is between negative pi over 2 and pi over 2. Well, if I take the negative of all three parts, remember if you multiply both sides of an inequality by a negative number, then the inequalities switch directions. So if I multiply each of those three parts by negative 1, then I can write it as negative pi is less than or equal to negative theta, which is less than or equal to negative 0, which is just 0. And then if I add pi over 2 to all three parts, I'm going to add pi over 2 to all three parts, so I get pi over 2 minus pi, and then pi over 2 less than or equal to pi over 2 minus theta, less than or equal to 0 plus pi over 2. It's just pi over 2. But pi over 2 minus pi is negative pi over 2. So I'm being redundant, but this will simplify to negative pi over 2 less than or equal to pi over 2 minus theta less than or equal to pi over 2. Okay, well, the tricky part is this case. If theta is not in the interval from 0 to pi, and if we want to evaluate inverse sine of cosine theta, we find an angle phi that's in 0 pi, in that interval, such that cosine of theta equals cosine of phi, and then the inverse sine of cosine of theta is equal to the inverse sine of cosine of phi, which is pi over 2 minus theta. Sorry, pi over 2 minus phi. Okay, here's an example. The inverse sine of cosine of 13 pi over 6 Well, using the cofunction identity, cosine of 13 pi over 6 is equal to sine of pi over 2 minus 13 pi over 6. But this is sine, this becomes sine of negative 10 pi over 6. We can simplify this further, but the important thing is that this angle is not between negative pi over 2 and pi over 2. So what we can do is we can simplify cosine of 13 pi over 6 by using a reference angle. So 13 pi over 6, if we rotate that, 13 pi over 6, we get 12 pi over 6 plus, I'll go ahead and wind it around. So 13 pi over 6 has a reference angle of pi over 6. Pi over 6. And so we can rewrite this expression, inverse sine of cosine. In the first quadrant, cosine is positive. So the inverse sine of cosine of pi over 6 and so what do we do now? Well, cosine of pi over 6, we can write this as inverse sine of pi over 2 minus pi over 6, which is inverse sine of, this is like 90 minus 30, which is 60. The 60-degree angle is pi over 3. Sorry, inverse sine of pi over 3. And this will equal pi over 3 because pi over 3 is in the interval from negative pi over 2 to pi over 2. Okay, let's do some examples where we could use triangles. We just have a couple of minutes left. Find the following. The cosine of the inverse sine of 4/5. So one thing you can do that might help, think of the inverse sine of 4/5. Inverse sine of 4/5 is the angle whose sine is 4/5. So if we use this as our angle, if the sine of that angle is 4/5, then we can use the Pythagorean theorem to find this side. This side will just be 3. My diagram doesn't look to scale, but we can use a right triangle. The sine of that angle is 4/5, and so the cosine of that angle, whose sine is 4/5, is 3/5. Okay, we'll do more of this tomorrow. We'll finish section 8.3 tomorrow, and then afterwards we'll start chapter 9, section 9.1. But that's all for today.